All right. Thank you for the introduction. It's great to be here. I appreciate the invitation to talk. I was going to warn everybody. Luke told me this is a real powerful laser. So if anybody falls asleep, I'm going to see how accurate I am. If it'll burn a mark in your forehead so everybody at the mixer knows who fell asleep. Not saying my talk's boring, but just be warned. Anyway, I do want to talk a bit about some of the things that we're looking at the university as far as a research perspective. A lot of these are in the developmental stages. They're not necessarily developed programs or projects yet, but they're different ideas some of our faculty have. There's a number of different faculty that contributed to this talk, ideas as well as some content as well. So I'm going to talk about how this can fit and where we see, coming from the university standpoint, we might have an application and we might be involved as well. How especially UAVs, this is where I guess you could say the rubber meets the road for a lot of growers. I'm an extension specialist. I do a lot of applied work. I deal with growers on a day-to-day basis. And for me, using it in the field, straight applicability of our growers is going to be key. And so precision agriculture is going to be the end goal for a lot of these different projects. We can observe, measure, respond to spatial variability within fields. A lot of growers are already doing this with sensors on machinery and on the ground. But we can also utilize GIS, GPS, and remote sensing. It's kind of the missing piece in tying this all together. A lot of the guys like to get that drone out, fly it around, they have a little fun with it for a few hours, and then it kind of gets packed away up in a closet somewhere unless the kids find it, and then usually gets wrecked. So we're trying to find where can we put value. And crop scouting, being a weed specialist, not the kind that kids get excited about, but killing them, not growing them. We see scouting as an option, right? And other pests, insects, and diseases fit in with that as well. We can pinpoint areas for inspection. If you fly over this field and you see, certain hot spots here, different colors, changes, you can say, okay, I want to either go investigate that on foot, pay a little more attention, or you can change your application with targeted sprays to enhance your efficacy or reduce your costs. If you don't have to spray the whole field, why bother spraying the whole field? It reduces your chemical input, it's more environmentally sound, and often more effective as well. Overall goal is to lower our environmental impacts. If we can reduce the amount of time, the fuel we're burning, time going out in the field, spraying, water used, chemical used, it has a lower input overall. And it gives us 100% coverage of the field. Oftentimes when we go out scouting, we'll do little Z shapes or W shapes. We'll just look at a fraction of the field. We might just kind of go across it one or two times. We don't see the whole field. We might miss some of the hot spots. So it gives us 100% coverage to see the whole thing, the whole picture going on. Other ag applications where we can find value, mapping crop residue. There's a lot of interest in using cover crops or reducing tillage. We can map this residue, see how much coverage we have and where we can improve or where we're doing a good job. Another, tile drainage. It's not a huge issue for us in North Carolina. We do have some as you get towards the coast, but the rest of the country, we do have a lot of tile drainage. You can see where the tiles are working, where they're not working, where you might need repairs, where you have low spots in the field that may need to be addressed. Another, when we look at crops, tiller density, looking at your overall crop growth and health, you can take a look, fly over that field, even with just a regular image, and see how that crop is doing, do some tiller densities, some counts, and do some general scouting quickly on the grower level. And then again, not something we deal with a lot, elevation changes in fields. We do have some changes as you go west in the state, but as you look at like rice production or areas that need terracing or waterways, elevation changes on the surface become important, mapping those, seeing where you have those changes so you can be most effective in your crop production. Some of the challenges we have out in, when you step out of the greenhouse, we have everything going on. Lots of times I do some greenhouse work and it's so much easier to me. I know there's challenges with it, but we have to deal with Mother Nature and everything she throws at us when we step outside. And the biological system can be so dynamic. We're relying on, I hit that wrong button too, relying on the sun for our light source to really generate a lot of that energy that we're recording and seeing. And what's going on in the sky, whether it's clouds that can scatter the light, you can have refraction and bouncing of the light, adjacent pixels giving you edge effect, affecting what's going on, or terrain shadows. So a lot of that factors in, and how do we account for this? Research so far has been really trying to focus on direct sunlight, a lot of it focusing on 10 to 2 o'clock during the daytime, getting that overhead light to give optimal reflectance. But how many growers have time to just dedicate doing their scouting right at 10 to 2 during the day? So that's some of the things that we'll have to look at going forward. There's 3 primary interactions of the light as it's hitting a plant. When we look at it, these aren't the only things that happen, but you got your transmission of light through the plant, absorption going in the plant, and reflection. You can have refraction and light scattering, other things going on as well, but these are the 3 primary ones we use when we're detecting our differences in plant phenotype. We look at the reflectance curve and on the plant canopy reflectance over here. You can see we've got down on the low end where we detect our chlorophyll in the visible range, but most of our measurements come in the near infrared and middle infrared. That's where we detect things like our leaf shape, leaf area, number of leaves, and plant structure. And that's all typically done here in the near infrared. In that middle infrared, we see a lot of water content. And often that's probably where we'd be taking that stuff from the greenhouse that Todd was talking about, looking at it in the field and seeing how these plants respond to different water stresses. Some of the platforms that are being used and have been used, on the ground there are a number of handheld sensors that researchers use to look at our different responses of our plants. There are vehicle-mounted sensors. The challenge with these is covering enough acres and getting out there, seeing that whole picture in a rapid enough time. It's not much difference. If you're going to walk a field with a hand sensor, you might as well walk it and use your own eyes. You'll see about the same thing most of the time. Vehicle-mounted sensors, you have crop damage, you have limitations as well. Aerial and satellite are preferred, but they have their different challenges as well. You got planes, UAVs, and satellites that we can use. Why we would focus on UAVs, and a lot of the researchers are leaning this way. We're putting in permits to do research on the research stations and look at them. The big 3 reasons: high spatial resolution, greater temporal resolution, and low cost. Okay, so we can really look at a small area, a defined area, quickly and repeatedly over time. That temporal resolution is important. I'll talk about it a bit more. It gives us a feel of a measurement gap. There are things we can't measure right now, or they're very difficult for us to measure in a timely manner. We can take snapshots and look at little things here and there, but we can't look at them on a big picture very effectively. Ease of use. You don't have to have a lot of training time to get someone who can fly a drone or a UAV. Everybody wants to learn how to fly one, and it's fun, and then you learn how to fly one, and then you say, man, I gotta fly this thing every day. But it's effective, right? It's easy to teach somebody. And the nice thing too is you can identify individual plants. You can look in a small area, see what's going on a plant-to-plant basis, not looking at a large area and averaging over plants. It's really this ground resolution that makes the big difference. With a satellite, we're looking at about a meter squared resolution, which when this came out, it was great. The first satellites were 30 meters square, and they were great for forests and large areas. Now they've gotten it down to 1 meter, which when that was happening was a huge deal. That was a big deal. I remember the first 1 meter squared imagery that came out, and you're like, man, I can see 3 feet by 3 feet. That's awesome. Well, then you start looking at what the planes can do, and you're looking at half a meter squared, so just under 2 feet by 2 feet, right? So you're getting on a smaller area, and that's nice because now you can start looking at localized plants, but you're still averaging over about a 2 foot by 2 foot area. We get with our UAVs a much finer resolution, effective 1/4 meter squared and maybe less. We might hear from our third speaker some advancements to that. So 1/4 meter squared, you're talking less than a foot by a foot. Now you start looking at individual plants. You can start looking at individual plant structure, leaves, what's going on in small areas. And as you look at planted rows, you can cover a lot of ground. The temporal resolution, like I said, is key, especially in research. It's great if you have a snapshot in time. I've got a little bit of research of stuff that I did in my master's degree, and I don't feel like I'm old enough to say this, but this was from 2000 to 2002. It feels like a long time ago, but I don't feel old enough to say that. But it was done with a plane and satellite, and it was whenever they could fly it. And so I got my data about 2 weeks to 3 months after they flew it, with no warning that they were flying it. I just had to assume. We gave them money, so they were going to do some flights, and it showed up. And boy, you talk about stressful masters, that stuff comes in about 2 months before your defense. But that's all we had at the time. If I had UAVs, I could fly it as I needed. And that, in the dynamic biological world that we have going on is important because a lot of these things change from day to day. They change with our environment. So we can't just say what I took as a snapshot on a random day in July is representative of this whole field. So, your chlorophyll content will change, right, as you have different environmental conditions. The leaf shape, your leaf area, your plant's actually growing, right? So if you can fly that over the course of time, which showing here, this is your leaf area index across the season from April to October, and you can see how that changes. If you're doing a flight every 2 weeks or even monthly, you get much better resolution. If you could do it once a week, you're getting finer resolution. You're seeing what's happening in that plant on a finer scale. Below it, here is the change in chlorophyll over time, again over a season. So you can see how that rises to a peak and drops back down. If we couldn't fly these UAVs on a tight schedule and when we want to on a narrow, in a small window every few days, this data would be very hard to gather in a field setting. We would have to rely on greenhouse information, and it's a great start, but putting it in a real world application to see what happens next is important. Number of leaves change as well. That plant structure, there's a number of folks looking at plant structure, how it changes throughout the season, how different environmental conditions affect it. I mean, just a simple diagram shows corn, as it grows from a seedling to a mature plant, that structure obviously is changing with height, but the leaf canopy structure, how that plant is holding its leaves, are they more upright, are they drooping, what's going on, can all be detected with our sensors. To give an idea, again, why the UAVs are going to be important, give a comparison I have no idea what everybody's background is, so I may be giving you guys slides you don't care to see. But looking at coverage area, first off, satellite, it covers the world. It just keeps going round and round. That plane is going to do a regional. You can get a lot of data. It's a big swath when it flies, but well, we'll see. It's regional, and your UAV is a field or a farm. You're going to control the area it covers. Resolution is going to vary greatly as well. Like I said, that satellite is in meters, 1 to 30 meters. That plane's going to give you feet, and the UAV is sub-foot. It's going to give you a smaller area. Payload, obviously, that satellite's quite heavy. The plane is as well. That UAV is pretty light and easy to transport. Deployability takes years to get a satellite ready and put out. Days for a plane, minutes or hours for a UAV. Total costs, again, there's an easy comparison from millions down to a few thousand, even a few hundred, depending on what UAV platform you go with. The challenge may be air traffic restrictions. I guess if you're building a satellite and launching it, you probably have government approval somewhere. But then the plane, you do have restrictions, and that UAV, there's still a lot of figuring out to do, but they're a little bit tighter, and we have to make sure we're going through the right steps. Flight time, again, there's differences, years, days, and hours to minutes for a UAV. Obviously, it depends on your battery. Technology, those satellites are proven, so are those planes, the sensors up there, we know what we're getting. There's a lot of questions about UAVs. How good are the sensors? How effective are they? How stable? Are you getting shadows? Are you getting blurs? What's going on with that? And that's where a lot of research is being focused. The keys, as I mentioned before, you're talking resolution, sub-foot, deployability, very rapid, and cheap. Because if you've ever been involved in research, it often comes down to time and space. You can multiply that by money however you want, because money factors in, but it all depends on how much time you have, or your grad students have, in my case, or how much space you have. If we had all the space in the world, great, we could do 30-meter blocks and just wait for that satellite to pass if time wasn't an issue. But when we're doing our research on, this is one field, one researcher has this field. You can see here there's about 10 plots across right here and 20 ranges. So 200 plots right here. You figure you got 4 replications in there minimum. There's going to be 50 treatments. You're talking quite a bit of work going on right there. How much time do you have to go through that? Can you, dedicate that over the course of a long period waiting for a plane, a satellite? Or if you have a UAV, you can do your readings and your sensing very rapidly. You might even be able to shrink them up to smaller plots like these over here and increase your efficiency and effectiveness. This is just an image I pulled off the internet, showing a researcher flying a UAV, but I thought it showed pretty well. This is often what we have for research fields. We have long, plots. Each of these are going to be divided up here, but you got replications going across here and different treatments going down. And, normally we go through and we evaluate one plot at a time, visually writing down our assessments. For me, and I'm sure my grad students in the audience get excited to see something like this. If they could tell me what the weed control was with a certain herbicide, or how different varieties were responding to different treatments, by just flying a UAV across that field once and doing it every week, it would increase our efficiency enormously. It would take several hours to go through and evaluate these by hand, and if you have multiple locations and multiple studies, it really adds up. It really impacts your efficiency. Currently, NC State has 2 locations where they're allowed to do, or we're allowed to do, UAV research. One is right near Raleigh here, just south of town, and then the other is out near Plymouth at the Vernon James Research Station, or Research and Extension Center. So we have the capability, we have the locations and the resources to implement this type of UAV research. Some of the activities going on, a lot of these slides had Rob Austin's name down in that bottom corner. He's in the soil science department, does a lot of work with remote sensing and precision ag. One of the studies he's looking at is flying multiple missions throughout the growing season using different platforms, really trying to determine what platforms and what sensors are going to be most effective for growers. So he's got the different platforms as well as the different sensors. He's calibrating them and validating them. So not only is he flying them and getting imagery, but he's also going into the field, taking tissue samples and doing handheld measurements as well to try to validate, see which ones give you the most consistent results. That's where a lot of this initial research is going to come in, validating the use of these, doing comparisons from one to the other, and ultimately, most growers will tell you it comes down to money, economics. So which ones are most economically feasible? Other potential areas that we would have, this is a lot of ideas, like I said, I got from other researchers. We can use a lot of these measurements, leaf temperature, leaf area, disease susceptibility, leaf number, chlorophyll content, plant morphology. These on the left, especially for breeding purposes. A lot of our breeders, the wheat breeder, soybean breeder, had a lot of input on these and thought they could utilize sensors that detected these things to really phenotypically map their populations. Not sure why the font's smaller on the side where I thought I'd have more input, but I guess it's fitting. Plant species detection, weeds are out there in that field. Herbicide application, either making them or detecting them. Pest detection, diseases, insects, mapping, nutrient content, and plant health overall. To give some ideas about these, now this is greenhouse type work, research that's been done, but this is showing thermal images of two different plants. You have one with a normal leaf temperature and one that's a mutant that's got lower leaf temperature and greater water loss. So if you could take this out to the field and our soybean breeder could image like this, he could detect the plants that are losing more water and most likely more susceptible to drought. He could select then the plants that aren't losing as much water and move those into his drought breeding lines going forward. Similarly, in wheat, I've been able to detect disease. This is screening early wheat varieties for head scab. So our wheat breeder has interest in conducting this type of research and determining where in the disease curve a lot of these diseases occur and severity in order to then in turn inform our growers so they can utilize that as well. Near and dear to my heart, weeds. Weed seedling detection. We can look at imagery and you look here, it's kind of hard to detect with the naked eye the weeds in these images, but you can do some processing and pick them out. And I want to emphasize the processing side. A lot of these images come out, with some pretty colors and you can, pick out some differences. But until you start doing processing, it's really hard to tell what's going on. You can pick out some things like, all right, these are a little bit redder, so these might be healthy vegetation. Those are bare ground control plots, so you know where to calibrate with your sensor. And then these, because I did the study, I know were treated with a herbicide, and they have a little bit different color. But unless you know the randomization, or until you run the processing, you can't tell what's going on. So you do image classification, and this is really the bottleneck, and this is what has slowed down a lot of research, and this is where a lot of work needs to go into algorithms. Once you start doing these algorithms, and this is just a simple clustering, it picks out that healthy vegetation really quickly. You can pick out that bare ground as well, and it'll tell you where the ones aren't quite so healthy. It picks them out quite easily. This is where a lot of the development will go. Rapid classification and grouping of our different phenotypic differences in our plants. So with that, I'm going to wrap her up and appreciate your attention.